we ultimately reach to this chapter 6. That is the last chapter of this book. So chapter 6 cover energy and numerical method. This week is last week, so I can only cover energy method. Let's go through. Introduction. So far, we have used differential equation to solve problem. Differential equation gives us the exact solution. So another approach to get some PCR, some critical load, bucking load, it is energy over numerical approach. So they gives us the approximate solution. Let's cover energy approach. By the way, I would like to compare energy and numerical method. If we will use energy approach, we just consider elastic range and perfect system. So we can get PCR. In energy approach, we assume some function and then we solve it to get PCR. There are two different energy approach. One is Rayleigh-Ritchie method and another one is Galerkin method. I'd like to just introduce Rayleigh-Ritchie method. Numerical method, we can cover elastic and inelastic, and perfect system, imperfect system together. In numerical approach, we make several segments of the beam and then we solve it. There are two ways, Newmark method and numerical integration method. Today I'll cover Rayleigh-Ritchie method among energy approach. Then what is Rayleigh-Ritchie method? This is a procedure. We assume diffraction shape that satisfies boundary condition. So secondly, we calculate internal energy. Another term is strain energy. It is called U. And then number 3, we calculate external energy. Another term is potential energy. This is energy come from the external load. So we call it external energy. And then we can get total energy, pi. Pi equal strain energy and potential energy. And then we take a derivative regarding pi is equal to 0. From this equation, we can get PCR. That is a procedure. I would like to show you one example. When you look at the example, then you can understand how to do. Example 1, you can see here cantilever column. It is subjected to axial force P. In order to solve this one, we have to assume deflection. This is x-axis, this is y-axis. So this is displacement, deformation, lateral deformation. It is called the V. V equal ax square. This curve, the shape is ax square. We assume deflection of this. And then let's go to second step. You have to calculate strain energy. If apply the axial force P, you have two strain energy. One is strain energy due to axial shortening. When you apply load here, P, then you have axial shortening like that. This shortening. As this P increase, this cantilever column becomes short a little bit here. Let's say that on delta A. That is shortening due to P. And then if P reaches to PCR, it shows suddenly buckle like that. If this beam has this kind of deformation, it has some bending strain energy. So from the shortening, you can calculate the strain energy like this. Your undergraduate study, you have learned this equation, right? Strain energy equation. P equal axial force, E elastic modulus, A is area of this column. And then you have to integrate from 0 to L, dx 1 over 2. That is the strain energy due to axial force. This one is when it buckle, it has deformation like that. This column has the bending strain energy. It can be written like this. You have learned in undergraduate course. So 1 over 2 integral 0L m square moment square ei dx. Yeah, that is the strain energy equation. Let's go down. In this strain energy, this is strain energy regarding some axial shortening. This is strain energy of bending deformation. At this moment, we are interested in only buckling, okay, not actual shortening. So we can neglect this term because the actual shortening occurs before buckling. So we only consider this term because it is related to buckling. Moment is EI curvature, right? If you input this one in this equation, the moment equal EI m square. So this square. So resulting equation is 1 over 2 integral 0L EI curvature square dx. So you assume the diffraction equation. To remember how to assume v equal a x square. V equal a x square. So v equal a x square. You take second derivative here. Then you can get v2 prime equal 2a. Right? So if you input this 2a where? Here. Then if you take the integrate, the resulting equation is 2ei a square L. It is your strain energy related to this term. That is procedure. Let's go to number 3. We have to calculate potential energy. Originally, this is some cantilever column. P applied here. Then you have shortening here. This is delta A before buckling. And then when it buckle like that. Then you have additional deformation, delta B. So delta A is related to axial force. Delta B is related to bending behavior. This one is axial shortening. This is bending behavior. So potential energy can be written VA, VB. A is regarding axial shortening, B is regarding bending deformation. Then potential energy, you know the equation P times some distance of moving. The moving distance is delta A, right? Yeah, that is potential energy. Then P times delta B. Delta B is moving distance due to bending, like that. If you see delta A equal integral 0L d delta A, right? Delta A can be written like this. So you can write like this one. So integral d delta A can be written like that. Do you know why? If we take out this part, this one is dx. So if we draw somewhat larger, then this one is dx. So actual strain is epsilon xa. Actual strain like that. So strain times length. If we multiply epsilon xa dx, what is that? This one, d delta a. Deformation due to axial force, axial shortening, axial displacement. So dx times strain. It is that equation. So this strain can be written du dx. We can written like that. Then let's look at delta b. Delta b can be written like this, right? Integral 0L d delta b. Let's consider dx. If we consider dx, then we have the theta here. This angle is theta. You have a slope here. You have a vertical gap here. Vertical movement. Okay, due to you have a slope here. So if this is dx, then this is dx cosine theta. dx cosine theta. And then d delta b means the displacement due to bending. So dx minus dx cosine theta. Then you can write like this. If you use the power series expansion, cosine theta is this. If you input this equation to here, minus, eliminate, and then theta fourth, it is two higher terms, so we can neglect this one. So we have only this term. If you look at here, d delta b equal, you have only this term, right? This one can be ignored. So you get the d delta b equal this one, right? Theta equal dv dx, right? Square. So dv dx is v prime square. So delta B equal, you have to take integral this term. That is equation. So your V equal delta B times P. That is V, right? So potential energy rules. Okay, so minus, right? So P over 2 integral 0 to L V prime square dx. That equation. When you calculate this potential energy, we ignore this actual shortening term. If you recall the calculation of strain energy just before, number 2, we also ignore strain energy due to actual shortening. Why? This potential energy also we ignore potential energy due to actual shortening. So we use the same way between strain energy calculation and potential energy calculation because we are interested in the buckling behavior. So we just consider some bending related term. By the way, this is a resulting equation regarding potential energy. V prime equal 2ax because we assume V equal ax square. So V prime is 2ax. If we input this value here, then you can get this one. Finally, you can get this result. That is potential energy. And let's go to next page. If you look at the total energy equal strain energy plus potential energy. Your strain energy calculated is this. Your potential energy calculate is this, right? You calculate this strain energy in number 2. This one is number 3, right? Then let's calculate PCR. You can take a derivative pi against a. So 2ei 2a, right? L minus 2 over 3p a square. So 2a, okay, L cube, like that. That must be 0. From this equation, you can get PCR. PCR equal the resulting, the one is 3ei L square. So exact PCR equal, as you know, pi square ei over 4L square, right? That is exact value. If you use the differential equation, you can get this PCR, right? But when we use the energy approach, you can get this value. They are same or different? Yeah, they are different. This value is 2.47. This one is 3. There are some considerable difference between two approach. So the error is 21%. This error is not negligible. Somewhat big error. So let's look at why the error is so big. This is discussion regarding error. So we assume some displacement is ax square, and then we calculate curvature double prime equal 2a. So that means the curvature is constant, like that. Some value 2a. Based on this calculation, curvature is 2a, regardless of this x direction. Just constant value 2a. But the real one is like that. Real curvature shape is like this. So when we calculate in this procedure, we use this curvature. This curvature indicate constant, but real one is not constant, like that. So our assumption has some problem. Our result have considerable error, like that. Do you think so energy method is not accurate? No. We have another way. Although we're using the energy approach, we have some method to overcome this difficulty. So I'll explain it in next lecture.